For part C, they want to know is what time between the times 0 and 8 is the amount of water at the pipe at a minimum. So we got to find where this minimum occurs. And so what we're going to go ahead and do is we got to look at the first derivative test, but we've got to start with what is the amount of water. So I'm going to go ahead and call it A of t. Let's just say it's the amount of water. And if you guys remember, so we'll have the amount of water, we're starting with 30, plus we got to add in how much is the water changed by. So we got to think about how much has the water changed by. And what the water has changed by in this problem, so remember net change is the integral of the rate, right? So from 0 to 8, or 0 to t, we'll say t because the time is changing throughout this problem. And we want the rate in which the water is flowing. And so remember, there's water that's coming in and water that's going out. So what we're going to do is we're going to do the inflow minus the outflow. And that's really the rate of the water and how much water, as far as how much water is in there, because there's some coming in, some coming out. So the integral of these two rates being subtracted is going to give you the net change of the water inside that pipe at that time. So what we're going to do next is we got to figure out where this equals 0 and test it. So this would be derivative of 30 is 0, and then derivative of that is just going to be r of t minus d of t, which we found in the last one. You know, the amount of water in the pipe was, at least the rate of it is r of t minus dt. So when does this equal 0? So I want to know when does r of t minus d of t equal 0. So what I'm going to do is I'm going to go ahead, let's just go ahead and graph r of x and minus d of x. Let me turn off the other two graphs. And we're really restricting between 0 and 8. You can see it's bouncing all over the place, but we care about between 0 and 8. And I have 3x in there. That's probably why things are a little crazier than they should be. So 0, and then also 3.272. So we have t equals 0 and 3.272. And then the next time it happens is after 8. Remember, our interval is 0 to 8 here. And so that's 9.4. So that's kind of out of the picture. So what we want to do is we want to test those values, figure out which one's the minimum. And you could see, is that a minimum? Well, yeah, it is a minimum because it's going from negative to positive. And I think that's actually a sufficient answer to go with. But we do need to consider the endpoints because from here it becomes negative actually. So from 0, 8, and then we're have a 0 right here at 3.272. So it's positive, so it's increasing out of this endpoint. Or no, it's negative. Hang on, sorry about that. It's negative. You can see that right here. Remember, this is the derivative graph, so it's below the x-axis, so it's negative there, and then it changes to positive, and so it stays positive from there. So increasing or decreasing out of the endpoint means that this is a max, and then right there means that this is a min, and then increasing into the endpoint means that that's going to be a max. So what you're going to have is you're going to have a min. So just to say the amount of water in the pipe is at a minimum at t equals 3.272. Now we have to double check, are they asking for when or are they asking for the amount? So they're just asking for when. And so the justification would just be this first derivative test. You can, say that the first derivative is changing from negative to positive. They want us to justify. So the rate of the water flow goes from negative to positive. And that should be a good enough justification for the minimum. You can always plug it back in and check different answers and explain that way.